Did I start too early? Oh, sorry, just a little coffee break. Well, okay, all right. Okay, so yeah, so everything has been said already. So I'm going to get around this problem by having a talk in two parts, two halves, and the geometry will be in the second half. But the trick, you see, is that the two halves add up to much more than one. So with a bit of luck, you won't get to hear any geometry at all, which really means that that's officially will be the end of your little 1-week vacation in California. So here's what I want to talk about. So I want to introduce some kind of a program of research which some students and I and other collaborators are thinking about, and it looks at a different look on what computation is. So traditionally, you have a function f you want to compute on input x, and what happens is f typically is too hard to compute exactly anyway. And so, I mean, for interesting functions, you can always multiply by 2. But so what people have done is, in order to get around this difficulty, and short of proving that p is equal to np, then you change the model a little bit just to make your life easier. So you say, well, we're going to allow random bits. So you change the model a little bit, and hopefully that will make life easier. And another way you can change things is by saying, well, instead of having the exact answer, then I'll be happy having something close enough approximation. So in the first instance, you change the model. And in the second, you change your expectations, basically, what will make you happy. Just lower your standards, lower the bar. And which is never hard to do. Now, what we're going to talk about is something that sort of has a dual approach, where instead of focusing on the output and tweaking with it to make life easier, then let's think of tweaking with the input and looking at what I call input-driven computing, where a lot of the story will be focused on this part. And there has been a large body of work, of which I want to review some of the most interesting work, on that sort of thing, or so what's called sometimes sublinear computing, or spot checking, property testing, sketching, where the basic idea is that you have perhaps a huge amount of data, and you cannot afford to look at it even once. So you can at best sample somehow, just take a very quick snapshot of the input. And the question is, can you compute f? Or can you compute f with some accuracy? Which functions can you in this way approximate, and which functions can you not approximate? Now, you see, what makes this interesting is that it's not so much this one situation where you have lots of data, and then it's just so big, you just can't really deal with the whole thing. But there's also other problems which fit neatly into this framework. For example, suppose the data is very imprecise, like this notion of priced computation, where when you want to look at the ith entry in your input, then you're given a knob which tells you how much accuracy you're going to get this piece of data, and there's a cost attached to this. So in the real world, this could be, for example, if it's biological data, the quick and dirty input could come from statistical simulation or something like that. And so, but perhaps that's not precise enough. So instead, you take some biological experiments like high throughput experimentations, which give you much more accurate data, but yet it's not perfect. So perhaps you really, really need to know precisely what this number is, in which case you may really have to spend a week in the lab actually doing the experiment. So it's really very important when you are confronted with this potential data to know how much price you're willing to pay for each input, because it'd be terrible to spend a lot of time getting some data and realize later on that this data was useless. And think about it, this is an old problem in computing. When all data is not equal, it turns out when you want to do linear programming, ultimately what matters is just a very, very small fraction of the input, which specify the answer, the optimal. I think if you know that ahead of time, you would not have checked looking at the rest. But of course you don't. It's the chicken and egg thing. So that's the sort of thing we're facing here. Okay. So of course, this is the old traditional thing. You've all seen this before. You want to take, an average of numbers. The canonical example, of course, you don't have to look at everything. Just take a small random sample, just do the average, and use this as your estimate of what you want. And sure enough, that if the variance is not too big, if these numbers are bounded or something like that, and then if you pick roughly 1 over epsilon squared, then with very high probability, say 0.9 and something like this, then you can guarantee the relative error will not be too big, will be bounded by epsilon. Now, notice something very important, which is that we have to retain approximation and randomization. So this is typical sublinear work, where you just look at a small part of the input, and then you just infer some output. But if you were not allowed approximation or randomization, there's just nothing you can do if you just think about it. Okay, so it's really crucial to have that sort of thing. Okay. So here's this nice notion. If you have some data, and you want to know whether it's sorted or not. So this is sorted and this is not. And you're interested in situations where things are far from being sorted. So you'll say the second one is a quarter far from being sorted, because it would take the modification of a quarter of the input to turn that into a sorted list. So you can define this notion of distance between input strings. So of course, there are many ways of doing this. Here, the way is the sort of edit distance, which is so there's some input and you're allowed to tweak a fraction of it. And you will say that so if it's sorted, then you know what it is. If it's epsilon far sorted, it means that no matter how you modify any fraction epsilon of the data, you will never make it into something sorted. Okay? So there's a really nice algorithm by those people that says yes or no, whether that's true or not. So the algorithm is 1 over epsilon time number of queries, and the time is epsilon minus 1 over epsilon log n. So that's the area of property testing. Well, I should also say that the algorithm is really cute. Briefly, here's what you do. So you have your list of numbers, and if it were sorted, then you could do binary search. So you pick index I, and there's the number AI, and do a binary search looking for AI. Now, if it's sorted in log n time, you're going to find it. Well, obviously, if it's not sorted, then sometimes you will find it, and sometimes you will not. And intuitively, the more unsorted it is, the less likely it is that you're going to find it. Okay? So that's the algorithm. You simply pick a few indices at random, and you do a binary search, and you just see whether you find what you're looking for. It's as simple as that. And you can prove that actually that does exactly the job. If 1 over epsilon queries into the data, each of them a binary search that costs log n, you can tell whether the input is epsilon far from being sorted. So this notion of property testing goes back to, yeah. Here you have the data in some array, say. So you have random access. You can say, in this model. There are other models where you don't have this. Property testing, so it goes back to Rubenfeld and Sudan. And so the idea, so you all know what a property is. There's some inputs, and some have the property, some do not have the property. So the inner blob are those inputs that do have the property. And now there's this notion of distance between input, instances, which I defined earlier. But there are many other ways of doing it, you'll see. And so you also consider the subset of inputs that have the property, and then the subset of inputs that are far away from the property. So again, it would take a lot of editing epsilon fraction of the data in order to get this to have the property. And there's this sort of no man's land in the middle, which it's in between. And now the thing is, you see, the algorithm now does not have to tell you exactly what happens. It simply is happy as long as the thing has the property. Then it says yes, or at least it says yes with high probability, so 2/3. There are various models. And if it's far away from the property, then it says no with probably 2/3. And of course, there are models where you change those things to be like, often this is 1. This is taken to be, to be equal to 1. It's a one-way, one-sided error. So you need a metric in order to talk about this notion of distances. Well, this has been generalized in some, but I won't get into this. Now, there are two questions about this, which is it an interesting notion? Well, that's question number 1. Question number 2 is, does it really make computing simpler? I mean, if you're just gonna, by tolerating this kind of error, you're just gonna, be able to shave a factor log in here and there from otherwise huge complexity bounds. It's not terribly interesting. Okay, so these are really the two questions, which are related. But so, of course, historically, I can't resist to mention this, that it really sort of started with the PCP theorem, which, so here's my take on this theorem. I wake up in the morning, and then I have, now that in the math department, I have a proof of Raymond's hypothesis in my head, but I want to convince you that I have this proof. But of course, I don't trust any of you, so I'm not about to give you my proof. So I'm going to write my proof in such a way that I will offer you this protocol. You can just look up a constant number of bits of the proof. In fact, only 3 suffices, which is amazing. And then you think how painful that can be. You go through that. But there's not that much to think about because you only have 3 bits or a constant number of bits. So do all the thinking you want on 3 bits. And then finally, if you form a protocol, then you will always accept the proof if it's correct, and you will reject with probability 1.99999 if it's a false proof. It's really a stunning theorem, I think. Certainly baffles the intuition how this could be true. Now, to make a very long story short, all this is about, really all this is about, is to rewrite a proof, a standard proof, as a code word. Okay, so you define some kind of code, and like an error correcting code. So you define some kind of code, and you just write this as a code word. And now the whole point is that the question you're asking is whether a given string given to you as an input is a code word or is far away from being a code word. And it turns out that the reason why we can do this in constant time is because of this property testing theory that I just talked about. So it's just, this problem of whether a list is sorted, this is just the same thing, just a little bit more complicated. Okay, so is that interesting? Well, yes and no. It can be trivial. So for example, suppose you ask, is a graph non-bipartite? That your property is not to be bipartite. So if it's non-bipartite, then your algorithm has to say that it is so. So it has to say yes, has to accept it if it's not. But see, the problem is that if your algorithm always says yes, always, it's going to be fine. You see, because if your graph is bipartite, I can just throw a triangle in it, and now it satisfies the property. So if you always say yes, you're right, because if it's non-bipartite, you see, with a very minute modification, the edit distance being tiny, just a triangle, then I make it true. And so that is just stupid, really. If all problems were of this sort, I won't be talking about this. But of course, as we'll see, that's just well, it's an exception. There are lots of problems like this. But there are plenty of problems for which it is interesting. So intuitively, if you think of geometry, is you really see whether the complement of the property has a core inside. Are there instances that are far away from the property? And the problem being non-bipartite is that there's no such thing as being far away from non-bipartiteness. Okay, it's like there's no such thing as being far away from being dead. You see, but far away from being alive, that's a very different story. What?
What does it mean that there's no such thing?
I don't talk together because you cancel each other. Some kind of
So what does it mean that there is no such thing as being close to?
Well, because if you are bipartite, with a trivial modification, I just add a triangle, and now you satisfy the property. So you see, you were not far away to begin with, wherever you were as a graph. I'm sorry to think of you as a graph, but it's Not even a directed graph, just an undirected graph. But lots of cycles, possibly, an interesting graph. And then whatever graph you are, you're always close to a non-bipartite graph. But that is not true the other way around. It is not symmetric if you think about it. Okay? You can be non-bipartite and very far away from being bipartite. It's a pretty hard word to pronounce, this bipartite. That's another question, which I'll get to in the next slide. Yeah, what's the model? What's the epsilon refers to here? Yeah, that's a good point. Okay, just hold on to for a second. Gorashi and Trevisan gave a whole bunch of graph properties that basically cannot be properly tested fast. That is to say, to test those properties, you simply have to look at the entire graph. And these are properties in NP. So again, if all properties were like this would be bad. So this would be bad, this is bad. But there are interesting things. For example, PCP is one, but to compute to test how big a clique a graph has, an NP-complete problem. Not just NP-complete, this is the hardest in the PCP theory of approximation. You can actually do this with extremely fast. In sublinear time, you can actually answer those questions if you're close from, say, having a K-clique. Same thing with coloring and so on. So that is really sort of amazing that you have this huge gap if you just allow yourself some error. Are there general techniques and principles that we could use, in geometry or in other things? So, there are just so many results. It'd be boring to just go through, all of them and try to make sense of that. So okay, here's graph being bipartite. So here's a beautiful algorithm of Gorashi and Ron. So again, let me address this question. Now, for this result, we consider a graph as being a collection of adjacency lists. In other words, there are nodes, and the nodes have pointers. For each node, there's a list, which show like pointers to the other. So it is not a matrix in this model, okay? This is useful, say, think of a graph just for example. It doesn't have to be that way. Say a D regular graph or 3 regular graph, or with small degree. Then the matrix would be a bad it would be mostly sparse, so that's not very interesting. But so now everything is represented by a little list with the neighbors, and the question you want to know whether it's bipartite or not, to coloring, okay? And so here's the algorithm is quite complicated, but there's one basic idea, and then lots of technical points. It's really cute. So how do we do this? Here's the algorithm, okay? Pick a certain number, pick one random point, like this vertex. Pick a random starting node, okay? And from that, you will start a bunch of random walks, okay? Just some random walks. For technical points, you put a self-loop. So when you're at a node with probability half, you stay where you are. And otherwise, you just go on your merry way. And so from the same thing, you spawn a whole bunch, square root of n times this, random walks, okay? Now, suppose the graph is mixing rapidly, and the length is about polylog over epsilon. If the graph is mixing rapidly, which really means that after this amount of time you've walked, this point here is pretty much uniformly distributed. It's pretty much like any point, any node in the graph. And then you see by the birthday paradox, if you pick root n elements from a set at random, then you're going to have collisions, okay? Some of them, you'll pick the same guy twice. So you do expect to land in the same node, at least once, maybe a couple of times or something like this. So you could repeat the whole thing, a few times, like log n over epsilon, to make sure there's at least polylog such things. And now you have little cycles. And you check the parity of the cycle. And I see if it's bipartite, it's always going to be even. So you just check the parity of all these cycles. If it's even all over, you say it's bipartite. And you won't be wrong if it is bipartite, because certainly you will pass this test. Now, if there's an odd cycle, then of course you'd say it's not. The problem could be that it's not bipartite, and yet you say it is, because you haven't been lucky. You've only encountered even cycles, even though there are odd cycles, but you did not find them. So of course there's possible error. But it turns out that if it's rapidly mixing, then if it's epsilon far from being bipartite, then there are enough. There's a large collection of odd cycles, and if there are enough odd cycles, these cycles are almost kind of random. So you're quite likely, in fact, to bump into one of those. And then you'll see it's odd and you say, aha, it's not bipartite, and then you'll do OK. So that's the sort of thing. So from this algorithmic specification of epsilon farness, all the proofs go like this. You have to show that there's a lot of something. There are a lot of witnesses. Like here it's odd cycles, but then it could be other things. And then the technical part of the algorithm is that if it's not rapidly mixing, then this doesn't work. I mean, think if it's a tree or something. I mean, you never find cycles, obviously. So, but then there's a nice result. There are nice results, so dual results of random walk theory that says that if in polylog times your random walk has not mixed, that is to say it's still highly biased where you've landed, then it means that your graph has small cuts. Okay, you can actually prove that, and you can find those cuts. And so what you do, and you cut the graph accordingly, and then you repeat for each part. And that gets a bit technical, but it's roughly the idea. And so.
But if you have a complete bipartite graph with just one X line.
What?
Suppose you have a complete bipartite graph.
Yeah.
With just one X line.
Yeah. So it doesn't matter.
I mean, how will you find it?
I will say it's bipartite, and I'll be okay. It's not, but it's okay. I just remove it, and then I'm fine. That's the trick. That's right. I mean, the fact you can modify this thing has heavy implication. Now, let me just say something about what you hinted. We didn't rehearse this, by the way. It's just natural wavelength sort of thing. What if you have a matrix representation instead of lists? How different are things? Now, really, this makes sense only for dense graphs, because now the epsilon will refer. Okay, maybe I should have been more specific. In the previous slide, the epsilon, what does it mean to be epsilon far? It means you're allowed to add or remove up to epsilon times the number of edges. Okay? Here, it's epsilon n squared that you will be allowed. So think of a matrix of zeros and ones, and you're basically any two that differ by only epsilon n squared entries will be the same graphs for all practical purposes. Of course, this makes sense only if it's a really dense graph, because sparse graphs, then they're all the same by this thing. Okay, but still. So how would you? I mean, the reason why I'm going through this, although it's not very geometric, but I'm really convinced that these principles, they're very, very basic, deep principles. They're very simple principles, but they're very, very deep and fundamental, I think, and find many other uses. I'm really convinced. So here you want to see whether a graph has a certain property. So think of it as a matrix. There's this paradigm, which sample and solve paradigm, which simply says, well, look, it sounds to me there's a trivial algorithm. You want to know whether the graph has a triangle or something, or not a triangle, or something like that. Why don't you just pick a random set of columns and rows, okay? Or if you will, take a random set of nodes and look at the induced subgraph of that, and see what happens in this property, okay? And then simply decide on that basis. So you extract a tiny sample of the graph, and you see whether there's a triangle or not. Depending on what you see, you answer the same thing for the whole graph. That's one paradigm. Now, the paradigm is a little bit more general. It says that you don't have to test the same property. It could be that in order to see whether a graph, say, is triangle-free, it could be, though it is not, but it could be that by this paradigm, what you would do is take a random sample of the nodes, take the induced subgraph, and then check whether, say, it has a square or a pentagon or something like this. So you check a property, maybe not the same original property, that's the trick, maybe some other property, but you just check one property. That's a paradigm. And there's this beautiful result by Goldrush and Trevisan that says this paradigm is universal. For any property that you can test in time that is independent of the input size. And we'll see there are plenty of such properties. Okay, so we test whether a graph has a property and say it's possible to do that independent of the size of the graph. Then if that is true, forget coming up with clever algorithms, this will do. This algorithm actually will work. Okay. So it's a very structural theorem. That sort of. So. I forget when I started. I guess it depends on who has a flight to catch or something.
You started about 25.
Okay. All right. Okay, 25. You know what? Like property testing, you want to find out how many people are bored here. You want to find if everybody is bored, plus or minus epsilon fraction of people. So this offers a paradigm. Take a random sample. But there's a much better way. It just came to me now. If you turn off the light and you see who reacts. If nobody reacts, that means they were very, very bored. Okay. I mean, they were asleep. You understand? It's, I guess, a little sleepy. Okay. So here's result of Nagala law. Is a graph H. So you have a graph, your input graph. And now you think of a tiny little graph H. It could be a triangle, could be a square, could be anything you want. And you want to know whether your input graph is H-free. It does not have any copy of H. And so there are two versions, either as induced or as not induced. Now here it's not induced. You just want to see whether you can see a copy of that. What Alain showed is that no matter what H is, there's a function which depends only on H and epsilon, which will allow you to test whether a graph is H-free in this amount of time. In other words, since it's independent of the size of the graph itself, then you can use the previous paradigm. So already we know the algorithm, okay? And furthermore, he characterizes, this is quite remarkable. He characterizes the nature of F. So F is the number, is the size, if you will, is the size of the sample graph you have to take. Okay, you pick random sample of nodes, and now you see, you take the induced subgraph of that, and you ask, well, how big F is. And F is polynomial if and only if H is bipartite. It's quite amazing. I'm sorry?
Polynomial in the size of H?
Yeah, exactly. Polynomial, right, in the size of H, and also 1 over epsilon, right, yes.
How do you know the algorithm?
I'm sorry?
You said you already know the algorithm. How do you know that?
Because I showed the algorithm. The previous paradigm says if you have this kind of complexity, then, or maybe you're asking a trick question. Oh, okay, yeah. So if you're asking the trick question, if you're asking the non-trick question, I have an answer. But I think you're asking the trick question. So the trick question is, if to prove this, he has a very complicated algorithm, I can just toss it and use the previous algorithm.
No, I think I'm asking.
Oh, you didn't ask that.
I don't know what property it is.
Oh, H-free.
Yeah, but you said you changed the property.
Yeah, right. So in the case of H-free, it's the same property. Yeah, right. Yeah. That's what you're. So it's neither a trick question nor a non-trick question. It's something like in between.
So is it an epsilon of a trick question or a non-trick question?
Oh my God, people are gonna miss their flights here. Okay, I heard.
Yeah, 1 week.
1 week. Okay. But then I'll just speak very slowly then. But did you have a question or just a grunt? Yeah, exactly. It's the size of, right. Yeah, exactly, of complete bipartite subgraphs and so on. And again, all these proofs are based on the presence of witnesses. You see, if you're far away from being H-free, there are too many negatives here, but if you're far away from being H-free, there has to be a lot of stuff. There has to be a lot of H's, basically, all over the place, okay, in some ways. This is not that hard. This is a hard result. This is sort of, this is the sort of stuff Janos likes. So this result by Alain, Fisher, Kriver, blah, blah, and those people, it says, well, what if the properties of the form there exists, for all So there exist 3 vertices so that for all pentagons, there are the following things true, okay, something like that. And then, of course, the reverse. Then they show that this is impossible, that there are cases like this you cannot test in constant time. And on the other hand, like this, you can test them all. So in particular, if you remove this, then you have H3 would be this, because it simply says H3 means that for any set of H nodes, candidate nodes, there is no H. So you can write a formula for H. So this result proves just this. But you can add this. There exists. And that is really complicated. It uses the regularity lemma and that sort of thing precisely to show, if you know a bit about the regularity lemma, there are all these consequences of the lemma that really show things about the abundance, the overabundance of certain subgraph of certain types. So that's the sort of flavor that's used. Now, why that's very useful is because, you may wonder, well, who cares? I mean, it's just, well, you care a lot because coloring. If you look at coloring, you cannot write coloring as a first order formula because it's really a statement about functions, not about actual variables and so. But what they show is that by using this notion of property indistinguishability, you see, if you have 2 properties, different properties, but it is true that any time you do not, when you satisfy the property and then you do not satisfy the other property, then I can modify you by epsilon to satisfy the other property. Say, suppose it's always true. Okay, so you have 2 properties A and B, and suppose it's always the fact that for any input, whatever happens to A, if you satisfy A and you satisfy B, then it's okay. If you don't satisfy A and you don't satisfy B, then it's okay. But if you satisfy A and you don't satisfy B, and then it's possible to modify U by epsilon so that you satisfy B. So now you agree on A and B. So if modulo epsilon modification, you agree on A and B all the time, then we'll say A and B are indistinguishable. That makes sense because see, for these algorithms, they are truly indistinguishable. You cannot distinguish those properties under this model, okay? And so coloring cannot be written in this form. However, it can be written. There's a property that is indistinguishable from coloring that can be written like this. And you need the epsilon. And that's how they show a result of this kind, constants for coloring. Which is really, I mean, now you have a stunning result because, this is NP-complete problem. And now you can decide whether something is close to be colorable in constant time. I mean, this is not even linear. This is constant time. It's quite remarkable. And there's been lots of extension of that.
Have in this case depend on K, right?
Oh. Oh. The number of queries it's all this crazy regularity lemma functions, like towers. Well, you know that stuff. Towers of towers of towers of.
And it has
Yeah.
K inside it.
It's a bit like when you look at San Francisco. There's just towers on top of towers and towers, and until a big earthquake comes and takes care of that. But so that's. No, so I don't think Intel and IBM are holding their breath. Like, oh my God, this is going to change our technology. Yeah, maybe not just yet. So, okay, enough for property testing. But again, there's an interesting. It's already. It's like, they've turned from computing to philosophy. Like theory of punishment and suffering and suicide. Okay, so there's an interesting duality between approximation algorithm and this sort of thing. See, approximation algorithm, you're saying, well, the output, you can tweak it a little bit. See this notion of distance, well, an approximation algorithm is just the same, where now you're allowed a distance epsilon on the output side. You're happy if you give me an answer that's 1 plus or minus epsilon. And here we're doing the same thing, but on the input side. Okay, so there is a duality of this. I mean, you can even do this in linear programming. I mean, either you can optimize a linear program with epsilon error, or you can do the exact computation, but you're allowed to tweak some of the input data. Maybe you're allowed to change a few bits to make your life easier. Now, these problems are dual, but they have completely different complexity. That's the amazing thing, because so in this regard they're very, very different from duality in standard optimization theory, because here this buys you a lot more than that. I mean, it's nice to make errors in optimization. It makes your life easier if you can put up with the error. But here, it's just a quantum leap, the difference. You go from NP complete to constant time, okay? So yeah, let me not get into the machine learning thing here. Okay, so now some of the previous algorithms, I should mention, do not simply say yes or no. They don't simply say, well, it's kind of well, okay, actually not those I mentioned, but there are other things like saying clustering and things like this, where if you really want, you get more than just yes or no. If you get yes, let's say it's k-clusterable or something like that, then actually it's possible to retrieve some kind of a cluster of clustering. Now, of course, not in constant time, but now you have to spend some time. But some of them, if you really go inside the algorithm, they give you a little more. So you can ask the general question, which is, well, can we compute functions in this way? For example, minimum spanning tree of a graph. So take a graph that has bounds on, say, the degree, d, and the weights on the edges, say, w. Okay? And you ask yourself, can I estimate the cost, the weight of the minimum spanning tree very fast? So these are constant, and epsilon is 1%. It's all constant. So you have this, the internet, and you want to see whether you can estimate the cost of the minimum spanning tree with the error 1% and constant time, just constant. And the answer is yes, which might be a little surprising. It's a simple algorithm, and there's been some recent application of this to geometry. So I get to use the word geometry for computing geometric minimum spanning trees, Euclidean. Okay. Yes. No, so now this is a different epsilon altogether. So yeah, I should be more careful here. Now we're back to the old model of computing. You don't change the input. Now, from now on, party's over. You just don't change the input anymore. The input is what it is. But you have randomization and you have approximation on the output within epsilon relative error. So that's standard, that's classical. What's non-classical is the fact that it's sublinear. You see, you have this huge graph, and you will only look at a constant number of nodes or edges or what have you. Also, the output, of course, yeah. So the output is a number, yes. I mean, that's a good question. Out of this number, can you actually get something? I mean, we've never been able to really make sense of this question, even though it's a good question, I think. But I mean, in sublinear time, of course, you're not going to get a tree. But maybe you can get something that, if you would, I mean, this is not a good candidate for this because minimum spanning trees are so fast. So, I mean, if you want a tree, it takes linear time, any tree. But then in linear time, you can basically compute the minimum spanning tree to begin with. So, or it could be if you have lots of edges, and then you want something that's linear in the number of nodes as opposed to the number of edges, then this would make some kind of sense, yes. I mean, that's an interesting question in general, to go, how do you go from an optimization where the output is the value that you optimize to what's the realization of that, okay? And so some geometry, if we want to hear, so this is stuff I did with Ding Liu, a student of mine, and Avner Magen, who is now at University of Toronto. Did a bit of geometry. We looked at simple problems in 3 dimensions. intersection, ray shooting. Let me show some examples here. Given two convex polyhedra, you want to know whether they intersect or not. Well, I mean, you got to make some assumptions. They're represented in with a facial representation or something like that, and your favorite face H-based representation, and so you can see whether they intersect or not in root n time. But again, you cannot actually output the intersection, obviously. I mean, you could if you allow more time, but certainly not within that amount of time. You can do things like ray shooting, point location, in Voronoi diagrams. Point location is interesting because we yet have to completely characterize the sort of planar subdivisions that can be point located in sublinear time and those that cannot. So again, remember, I mean, point location, if you allow preprocessing, and then you can do it fast. But here, you're just given this thing. And from the minute you look at it, the clock starts. So there's not much you can do. I mean, in fact, it's almost structurally interesting from the algorithmic point of view because there's so little you can do. There's not that much the algorithms. And there's not a great variety of algorithms because there's so little to do. I mean, it's like previous examples. If you have only 3 bits, I mean, how many algorithms do you know on 3 bits? It's a very small number. So other things, approximating the volume of a 3D thing in within small error. You can do this also in root n time. So root n also is the sort of magnitude. And these are all optimal, more or less optimal bounds. So root n really is the right answer. And okay, something where you guys can work on because this is not optimal. So this is this problem here of computing shortest path on a surface of a polyhedron in 3D. So you have P and Q, and you want to approximate the shortest path from P to Q. Actually, you want to output also some kind of a path. Now, if you want to do this in sublinear time, you see, you're going to have to fly over. I mean, just think of the polyhedron as Earth. You just cannot take a horse and just go from P to Q because that cannot be sublinear. I mean, it could well be that you go through a linear number of edges, and that's just the output. But if you fly, then it's different. You can just go fly into a triangle and just come back, or just fly with a few hops, and now you can actually output a path, which is a flying path. Or if you go through the Earth, you can go to China by flying, or you can go, like you dig a hole. So these are the models we're talking about. Very realistic. But it is. I mean, to have this thing going outside makes perfect sense. So the story is Joe Mitchell here?
So there's an oracle that is used for each point. So what is the...
Okay, so here the input is your polyhedron, and then P and Q, these 2 points. And the output will be 2 things. It will be first a number that gives you the length plus or minus epsilon, and then it will give you a path, a 3-dimensional path.
What is a crash? What is a... So what does it mean that it's not a polytope, right? It's a polytope.
Yeah, I didn't say that. It's a convex polytope. Yeah, sorry. Oh, maybe I never said that. Yeah, you're right. I never said that. It's a convex polytope. No, so you can, if it's non-convex, that's a very interesting question. There's been lots of work on non-convex. People in this room have worked on this. And so there are lots of open problems here. So our complexity is epsilon to the minus 5/4 root n. And I mean, this 5/4 is just, cannot be the right number. And I mean, it's probably more 5/5, the right answer. But whether epsilon should be multiplicative with root n is also a good question. Now, this thing here also is a good question. I mean, this is f of, so what's f? F is the best known algorithm for computing the exact, not the exact, within epsilon. But, the best, fastest algorithm for computing the shortest distance from P to Q within a small error of epsilon, or even the exact. So I don't know what the status of this is. Kapoor claim and log squared n. Maybe by now it's proven true.
So what does it mean that the function of epsilon to the minus f?
With this? Yeah. So f will be whatever you guys have produced as the best possible algorithm for the exact problem. And now I'm going to take this number and this function and just plug it in. And so n squared is an agreed upon bound. That stuff is really complicated, this thing, those geodesics on surface of polyhedra. It gives headaches. I mean, it's really a mess. So, you know, to see whether those things really work actually takes a bit of patience. And so everybody agrees on this. I mean, I don't know this one, maybe this is true. Joe Mitchell has doubts, but then Joe believes in the bound. Is Joe here? No. He knew better, yeah. And so, okay. What? Okay, but whatever f is, it's still unlikely that this is optimal. And I think it would be very interesting, at least to reduce the 5, you know, this exponent to just 1 over epsilon. You've worked on this. Do you believe this?
I take the 5th.
The 5th amendment or the 5th exponent here?
Both.
Both. Okay. Should briefly mention, I'm running out of time. Yeah? But you stole my time. You really did. I should be done by now.
No.
Or psychologically, yes.
You have more than 10 minutes.
Okay, all right. Okay, then I can tell you if you want. But let me finish my thing first. And then we'll see those of you who actually want to hear that thing, I can stay. Yeah, I actually want, okay, let me just mention these results quickly. Matrix approximation. Again, you have a large matrix. Can you find an implicit representation of a matrix using very few parameters? So for example, you could pick a random sample of the rows, or maybe the columns, the intersection of that, or not the intersection, the rows and the columns, make a matrix out of that, and argue that the singular values are about the same or something like this. So can you approximate the spectral, you know, spectral thing of the spectrum of a matrix? And so those people have done this, and it has all sorts of application for max cut and graph problems. Oh, the thing I mentioned earlier. It's funny how some of this work on sublinear algorithms tends to have a superlinear number of authors. It seems to be some kind of bound here. So there's this long thing here. On Euclidean MST, okay, where you actually, right, and these results make some assumptions which are, okay. I mean, you wish you simply had n points, and that's the input, and you can just look at any point you want. But that's not the way it works. You need some range query oracle that says, you know, here's this rectangle. Tell me whether there's a point inside or not, yes or no. And we assume that we have these oracles. Otherwise, you cannot do it. Some work by Piotr, Trindick, and there's people on clustering where the notion of sublinearity is not obvious at first that it's sublinear, but it is. So what they do is, you know, they do clustering in higher dimensions. You have n points in higher dimensions, and you want to find nice clusters for those things. And the complexity will be a function of the number of points. It doesn't sound sublinear, but it is, because the input, you see each point, since it's in high dimensions, each point will have, you know, d coordinates, and d can be quite large. So the complexity is really less than the input size. So in this way, it's sublinear. But I'm not sure I really want to go into all this messy thing. I'd better tell you more about this little program of ours, with the sort of thing that we want to look at. So again, this input-driven computing, the story is really to look at what comes in and try to make some assumptions in the model or in the specification that's going to make your life easier. So, well, there's a standard model called streaming, where there's been a lot of interesting work, where there you just assume that the input just comes to you like a signal, like a TV signal, a video signal or something like this. And then you can look at it only once. So it's not sublinear because you can actually look at the entire input, but you look at it only once. And you cannot record it, okay? So that leads to this notion of sketching, which is you see all this input passing by, and then you build some kind of small data structure that represents, I mean, of course, it's much smaller than the input, so you've lost lots of information. But your goal is that once you have the sketch, say you can answer nearest neighbor queries with some error, obviously, since you don't have all the information, but sufficiently accurately, okay? And these are really all sorts of fascinating questions, very much related to all the work that has been done on low distortion, metric embeddings, and that sort of thing. Price computation is some work also we've started doing. That's not new. I mean, there's been some work before on this, and again, that's what I was saying, that there's a cost, there's a different cost for, you're looking for some information, all these books in the library, and you're going to be charged for the books or differently. Or maybe these are web pages that you have to pay, for access, and you pay different amounts for different web pages. And the question is how your algorithm should go about it. A better example is probably archived information on the web. Say if you have CNN or something, so you may have a cached version of a site which you're interested in, and now there's the constantly updated original, but that is of more difficult or more expensive access, but you have access to a cached version which is a little old, but maybe not terribly old. And the question is to know when should you actually pay the price during the computation. Okay, so if you want to know, who won Red Sox or the Yankees, then presumably you want something reasonably recent. If you want to know what's the capital city of Italy, probably okay to have slightly more out of date. Although if you ask who is the prime minister of Italy, then of course requires a very, very accurate sort of thing. Uncertainty. There's been some also interesting work by various people. I cannot mention them. On uncertainty, where there you're given an interval. So the queries say, I mean, geometers are very familiar with this. So the input now says a bunch of points. For each point, there's an interval, and you know that the point lives within that interval. Okay, so we all know of this interval arithmetic and so on. But the difference is that if you really need to go and resolve the differences between values that compete within the same intervals, then you can pay extra, do extra work and actually increase the resolution and just go further doing that sort of thing. So another work I want to mention with Neer, Elan, and Ding Liu is, let me mention this, which is so you want to do high dimensional nearest neighbors. So if you have endpoints in very high dimension, and there's all these clever techniques of sort of random projections. You project the points randomly onto a log n dimensional flat or something like this. Then roughly the metric will not be too much distorted, and so you can do your near neighbor location, down below, much faster, and then sort of infer some sort of semi-accurate information for the original nearest neighbor. So what happens usually is that you say, what's the nearest neighbor of me? And Sariel is, but I get Janos. And the error there is that maybe the difference here is a factor of 2 or square root of 2 probably. It's always square root of 2. And so there's some ratio, which would be 1 plus epsilon, between these two distances, the optimal distance and the not so optimal. Sorry, don't take this personally. The not so optimal distance. And so you see, epsilon. Now, what if the epsilon is different from everybody? I mean, perhaps it is so damn important for me to know if Sariel is my closest neighbor. I've got to know that. I mean, I just cannot get that one wrong and ask Janos instead. So perhaps this epsilon is very small, or even 0. And some others, I don't care. You're my nearest neighbor. I got somebody 5 times further. I don't give a damn about it. So your epsilon is just, and so you have these different epsilons. And the question is to know, does it make any difference? Can you actually can you actually retain the benefits of when all the epsilon are the same and yet accommodate all these different things. Online learning geometric optimization is also something that's really cool where, say, where that's the talks this morning about learning manifolds and that sort of thing. I mean, you don't know anything about your input and you're computing something, some function you want to optimize, some geometric data, and you want to optimize this. And okay, so you just crank your algorithm, and then you find out that it gives you the answer, and that's it. Like, it lives in some ambient space of high dimension, right? But see, I mean, your algorithm, in fact, it depends on the dimension. If the dimension is small, it's faster than if it's very high. But maybe your thing lives in high dimension, but as we saw from Uli Wagner's talk, that maybe often those things really live in the subdimensional things. So, I mean, so you could go the sort of thing that was discussed, which is just go and learn the manifold, and then once you have this, just do your work. But suppose this data just comes online. You don't really have time to do that, but you want to get a sense of what happens if it's heavily biased away from being uniform. So say the points are in dimension 100, and maybe you assume first they're uniformly distributed, and you use the algorithm that's based on that. And then you realize after a while that the points tend to be really clustered around some kind of a 5-dimensional thing. Well, then you see you want to change your algorithm, and which will be faster because now you're in lower dimension. Of course, you could be wrong because the data keeps on coming, and then it turns out that it fills space. So you want to use some machine learning technology, online machine learning technology, to learn enough to fine-tune your algorithm. But see, the goal is not to learn the manifold. That's not the goal. The goal is only to know enough so that you can fine-tune this other algorithm which you have, which does whatever you want it to do. So this is the sort of thing we're talking about. Do you really want to hear the thing?
Yes.
I mean, don't do it for me. I mean, I can. My ego will take a no answer.
Give us something.
Well, excuse me, not my ego. It will take something. Give something. Were you?
The bus leaves at 3:30. What can you tell us by 3:25?
Okay, here's a sublinear talk. No, this is the wrong set of slides. Are we getting paid for this?
I hope so.
Oops. Okay. Okay, here's the question. Okay, so you can try to improve this. That has nothing to do with sublinear thing. It's just geometry. Okay. So here's an open problem. You have a polyhedron, convex polyhedron in 3 dimensions. Okay, and you want to wrap it by another convex polyhedron that's around it. Okay, that encloses it. And you want the house of distance between the boundaries to be at most epsilon. So you don't want this green thing to ever go further than epsilon from the black thing. And so a very tight kind of thing. How small can the green thing be? Okay, I mean, if epsilon is 0, obviously it has to be p, so the green will be the same thing as the black. But as soon as you allow a little epsilon, then presumably you can start using fewer vertices, fewer faces. So we showed that a bound of 1 over epsilon to the 5/4. So that's an interesting open question, I think, is to improve this. I mean, it'd be great to show 1 over epsilon. Yeah. I mean, the diameter. Yeah. Yeah, I mean, you assume the whole thing has, like, 1 diameter or something. Yeah. I mean, you normalize things, yeah. So.
You normalize by the area or by the...
Yeah, it doesn't matter. Yeah, 327, the kind of questions you're asking is beyond belief, It's
Do you assume an inscribed or no inscribed?
No, the black is inside. Isn't that obvious from the picture?
No.
I mean, even like this, it's...
No, whether you assume that there is a
Yeah, yeah, yes. Yeah, yeah, the whole thing lives inside a sphere of radius 1, say. Yeah. Yeah, 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 yeah. So, right. No, of course, it does not. Right. So you've got to Dudley, and then you've got to do so Dudley. Well, if you don't know what it is, too bad. There's a way of sampling this black thing with, just think of sprinkling this with red dots, and for each dot, take a tangent plane. Okay, and I use that as your thing. Okay, that's not going. I mean, that's going to